Welcome to this lecture on the basics of neuroscience. Today, we are going to explore the meninges. The human brain is an incredibly powerful organ, but it is also extremely fragile. In this session, we will discover the brilliant biological packaging system that nature designed to keep your brain safe from the bumps and impacts of everyday life. Let us dive in. To understand why the meninges matter, imagine shipping a highly fragile glass vase across the country. You would never just throw it into a hard cardboard box because the first bump would shatter it. The human brain is exactly like that fragile glass vase, and your skull is the hard cardboard box. The meninges act as specialized layers of biological bubble wrap and tissue paper. Without them, every time you nodded your head or went for a jog, your soft brain tissue would smash against the hard bone of your skull, causing irreversible damage. Now that we understand the purpose of this packaging, let us look at its structure. The meninges consist of three distinct membranous layers encasing the central nervous system. The outermost layer is the dura mater, a tough, leathery shell firmly attached to the skull. Beneath that is the arachnoid mater, a spiderweb-like middle layer that creates a crucial open space. Finally, the innermost layer is the pia mater, a microscopically thin membrane that tightly hugs every single fold and groove of the brain. Together, they seal and protect the delicate neural tissue. Beyond just physical layers, this system relies on a special liquid. The open space created by the arachnoid matter, called the subarachnoid space, is filled with cerebrospinal fluid. This fluid physically floats the brain, reducing its effective weight by about 97%. This buoyancy is critical for structural integrity. However, this closed environment also has vulnerabilities. If these layers become infected by bacteria or viruses, it leads to meningitis, causing severe swelling and dangerous pressure. Understanding this fluid dynamic is essential for treating head trauma and brain bleeds. How exactly does this fluid-filled system protect against physical impacts? We can understand this brilliant biological design through the fundamental physics of pressure. The formula is P equals F divided by A. Here, P represents the pressure exerted on the brain tissue. F is the force of an impact, like hitting your head on a doorframe. A is the area over which that force is distributed. Conceptually, the meninges take a localized force and spread it out. Because area is in the denominator, as the area increases, the resulting pressure on the brain drastically decreases. Before we move on, let us see this with a concrete example. Imagine a person bumps their head, generating an impact force of 500 newtons. If the brain had no meninges and hit the skull directly, this force would be concentrated on a tiny area, say 0.001 square meters. We substitute these values into our pressure formula. Dividing 500 by 0.001 gives us a massive pressure of 500,000 pascals. This immense pressure concentrated on one tiny spot would easily crush delicate neurons and cause severe traumatic brain injury. Now that we have calculated the unprotected pressure, let us prove how much protection the meninges actually provide. We will set up the calculation for the protected brain. The impact force remains exactly the same, at 500 newtons. However, the meninges and cerebrospinal fluid act as a cushion, distributing this same force over a much larger area of 0.05 square meters. We substitute these new values into our pressure equation. Notice how the numerator stays the same, but the denominator is now significantly larger. Continuing our derivation, dividing 500 by 0.05 gives us a protected pressure of only 10,000 pascals. By comparing the two results, we see the pressure drops from 500,000 pascals to just 10,000 pascals. Mathematically, this is a massive 50-fold reduction in stress on the brain tissue. This proves why the meninges are vital for survival. By simply spreading out the force over a larger area, they turn a potentially lethal blow into a minor, harmless bump. This mechanical advantage brings us to another crucial concept, the Monroe-Kelly hypothesis. The skull is a rigid box made of solid bone, meaning its total internal volume absolutely cannot change. Inside this box, the total volume is made up of three components: brain tissue, blood, and the cerebrospinal fluid held within the meninges. Because the skull cannot expand, if one of these components increases in volume, another must decrease to compensate. The meningeal spaces act as a dynamic spatial buffer to maintain this delicate equilibrium. To quantify this rigid environment, we use the intracranial volume formula. Conceptually, it simply states that the sum of the parts equals the whole. V sub T is the total intracranial volume, measured in milliliters. This must equal V sub B, the volume of the brain tissue, plus V sub L, the volume of the blood, plus V sub C, the volume of the cerebrospinal fluid. If the total volume, V sub T, is exceeded, it causes deadly pressure spikes that would crush the brainstem. Therefore, V sub T is an absolute physical limit. Let us apply this formula to a healthy patient to find their baseline volume. We are given a normal brain volume of 1,400 milliliters, a blood volume of 150 milliliters, and a cerebrospinal fluid volume of 150 milliliters. We want to find the total intracranial volume. We simply add these normal volumes together. 1,400 plus 150 plus 150 gives us a total volume of 1,700 milliliters. This 1,700 milliliters is the fixed capacity of this patient's skull. Now that we know the fixed total volume, let us prove how the meninges buffer against internal changes. Suppose a tumor grows inside the brain, adding a new mass volume of 50 milliliters. Because the skull is rigid, the total volume must remain exactly 1,700 milliliters. We set up a new state equation that includes the tumor volume, V sub m, and an unknown new fluid volume, V sub x. Plugging in our known values, we get 1,700 equals 1,400 plus 150 plus V sub x plus 50. Let us complete this derivation to find the new fluid volume. First, we simplify the right side of our equation by adding the known volumes. 1,400 plus 150 plus 50 equals 1,600. This gives us 1,700 equals 1,600 plus V sub x. To isolate V sub x, we subtract 1,600 from 1,700. This simple algebraic step leaves us with exactly 100 milliliters. The cerebrospinal fluid volume had to drop from 150 to 100 milliliters, squeezing out into the spinal column to make room for the tumor. Having proven the mechanical and spatial importance of the meninges, let us look at exactly how they are arranged. In this cross-section diagram, we start at the top with the hard, rigid skull bone. Immediately beneath it is the tough dura mater, acting as the first line of defense. Below that, you can see the web-like arachnoid motor spanning across the subarachnoid space, which is filled with the protective cerebrospinal fluid we just calculated. Finally, notice the delicate pink pia mater tightly tracing every single fold and groove of the brain tissue below. This is your ultimate biological shock absorber. We have covered a lot of ground today, so let us summarize the key takeaways. The meninges are the three protective wrappers of the central nervous system: the dura, arachnoid, and pia mater. Together with the cerebrospinal fluid, they float the brain and act as biological shock absorbers. By distributing physical forces over a wide area, they drastically reduce the pressure of impacts. Furthermore, they provide a flexible volume buffer within the rigid skull, ensuring our fragile neural tissue survives the physical demands of everyday life. You now have a solid foundation in the basics of neuroanatomy.